Let's talk about the trapezoidal rule in this recording. We are going to use trapezoidal rule to pretty much calculate the area. In many cases, we may have a curve and we may have a graph, and we would like to calculate the area under that graph, or in case we have more than one graph, we may want to calculate the interface. We may want to also calculate the area that is enclosed by um, more than one graph if we know that equation for that particular graph. So the trapezoidal rule is really an approximation method in which we can calculate basically the area under a curve. We use that and we apply it in calculating the areas. So I'm going to briefly go over the trapezoidal rule and do a few problems for you today. So as a trapezoidal rule states, if you have an integration of a form listed here, okay, if I can highlight it now. Okay, if you have an integration of this form, we would like to integrate from a to b over the entire function, and we would divide this function into different points, and we at different points we would actually find the coordinate of those different points, and we would actually use the trapezoidal rule to do so. As you can see here, the rule is given here. H is the length, which is b minus a divided by n, and n is the number of sub-intervals that we are going to use for that. So let's say if you have let's start looking at one example, example 1t. If we have an integral of such a form, again, this is the simplest, a more simpler form of the integral. As you can see, we would like to integrate this function over a range of 1 to 3, and the number of steps are 4. So what we would use here in this case, let f sub x to be 2x minus 1, and a would be 1, and b would be 3, right? So we set that up. Now we need to find h. In this case, h, again, let's take a look at the formula. It's b minus a divided by n is 3 minus 1, and n in this case is 4 because we are going to use 4 steps. So that would be h. In this case is half. Then we would complete the following table. So we simply plug in points. We're going to give different values to x to see what would be the value of our function. So if x is 1, the function would be 2 minus 1. If the function is 1.5, the f would be 2, and so on until 3. So that is pretty straightforward. Then we are going to plug in the values to calculate the area using the trapezoidal rule. So let me go back to the equation and compare what I have with the equation here. So here's the equation. I'm going to copy this equation. I'm going to bring it down here so it is much easier to reference to it. Okay, so there you go. So let's make a direct comparison. H over 2, in this case h was half over 2, y 0 when we plug x of o or x of 0, and the corresponding function was y sub 0, so that was 1. Remember up here we just did that and we tabulated in that table. So x of 2 is when we plug in number 2 as our x, and y turn out to be 3. Again, we are using this table to simply build our area. Pretty straightforward, really. The other example that is perhaps more applicable is also this example. We are using the trapezoidal rule. We try to estimate the integral t cubed plus t dt from 0 to 2. We are using 4 steps. Again, we would let f sub x to be our function, in this case x3 plus t, or simply you can keep that function the way it is. Instead of x of 0, then you're going to have t sub 0, t sub 1, t sub 2, t sub 3, and t sub 4. This just gives it more sense, really, as far as what we are concerned. Remember, we are dealing with engineering, and it's different than mathematics. We use mathematics as our tools, but we are not mathematicians, right? So we use that, and we build the function, and we would plug that in as such. Okay, there we go, 6.6. The one that is of particular interest to some of you, since it maybe it is really what you would be doing, is that example T3t. If we use the trapezoidal rule, we would like to estimate the integral from 0 to pi sine of t dt, and we're going to use 4 steps. So the first thing is we let f sub x to be sine of x. A is 0 to pi, so b would be pi. H would be simply pi minus 0, that's b minus a, divided by n, which is 4 in this case. So h would be pi over 4. Now we're going to complete the following table, as you can see, and we're going to give different values to x, and we calculate the function. We try to find the value of the function. So for every given x, there would be the value for that particular function. We're going to substitute x inside our equation we have here. So for example, if since the function is here sine of x, if we give x 0, that would be sine of 0, that would be 0. Then pi over 4, sine of pi over 4 would be 1 over square root of 2. Then next step is, again, we keep increasing that because we need to do this in 4 steps. So we simply divide 0 to pi into 4 areas. And if, for example, the x is pi over 2, then sine of pi over 2 would be 1, and so on. And remember, we can also use a shortcut here because it's symmetric, and you can also use this symmetrical trick, or the trick of symmetry. You can use that to solve your lab work, or a part of your lab work. So we substitute that. Again, we use the value of t the formula that I was given up here. I'm going to again copy this. I'm going to bring it down here for the ease of reference. So let me just go down here. So now I brought this down here again. Pretty straightforward. In this case, h is half, and h over 2 is 1 over 4th or a quarter. Y sub 0 is 0. 2y1 is 2 times y1. Remember, y sub 1 corresponds to x1. When we plug x1 into the function, y sub 2 corresponds to x2, and so on. One trick that we might want to play in some occasions is we can divide this area using symmetry, and we can simply calculate our equation. So here, for our case of the sine, we do the same thing, and we can pretty much plug in, as you can see in this case, 2 multiplied by 1 over square root of 2 This is symmetric, so we could simply, if we assume 2 times 1 is the center line, and then as you can see there, mirror image on the right hand side and left hand side of 2 multiplied by 1, and as you can see, we could have done a trick and simply substitute that by multiplying that by 2, and that would give us the final answer that we have in this case. If I want to compare the error that's associated with this approximation method with the closed form solution of the integral, I would have to actually integrate and take the value of that and bring it back in here and compare it with this equation to calculate the percentage of error for the final answer. We can also use MATLAB, other types of software that's available out there to check and come up with the answer. Excel would also work, and so on. But we are going to use those only as verification purposes at this stage. That is really all that I wanted to discuss today. If you have any questions, let me know. Thank you.